Okay, a box weighing 40 kilograms is pressed against this wall. The force, so there's a force applied to the box, right, diagonally at a 30-degree angle from the surface of the box, okay? If the coefficient of friction between the wall and the box is 0.35, what would be the minimum force required to keep the box stationary and prevent it from sliding down the wall? All right. So, I mean, this is a situation that we've probably all experienced in our lives at some point, right? Like you're helping somebody move, or you're like kind of juggling some heavy object in a hallway or something, and what do? You put it against the wall. And essentially what you're doing here is you're using the frictional relationship between the wall and the box to support some of the weight, at least momentarily, until you get your bearings. So this is another one of these problems where we need to sort of just start out by taking stock of all of the different force vectors that are acting on this object, right? With the understanding that when we add them up, they should equal something. It's something that we're going to think about right now, right? We should know what they should. We should know what they should all equal when we add them up and sum them, and then knowing that, we can create an equation that will allow us to solve for the variable that we don't know, which in this case is f, okay? So what we're asking here is just what f has to be in order to prevent this box from moving. It's not sliding up, it's not falling back down again, it's just sitting still. So if it's just sitting still, I think we can all agree then that the acceleration of this box would basically be 0, right? And what does Newton's second law tell us about things that have a 0 acceleration, right? Well, the second law, Newton's second law of motion, says that the sum of all forces acting externally on an object will be equal to the mass of that object multiplied by the acceleration of the object, right? So if we can agree that the acceleration is 0, well, if this is 0, then the sum of all forces acting on the object must also be 0, right? This is 0, that must also be 0. There's no other thing that this can be, right, if the box is not moving. And this would be the case if this were moving at a constant velocity as well, right? It's just in this case, the constant velocity happens to be 0. But if it were 1,000,000 meters per second, and that were not changing, the acceleration likewise would also be 0, and the sum of all forces would again be 0. Okay, so the fact that it's stationary is not entirely what leads us to conclude that there is a 0 acceleration. It's just that the velocity is not changing. Okay, so what we can do here is we can make a table, and we can describe every single force vector acting on this object in both the x and the y axis. Then what we can do is we can make one big equation that's all set to 0 and that adds each one of those vectors up with one another. And then since it's set to 0, right, we can use that equation to solve for f. And that's basically what we're going to do. But what we know here is that the sum of all forces in the x-axis will be equal to 0, and the sum of all forces in the y-axis will also be equal to 0. Okay, so let me just erase this real quick. And before I make this table, let's just investigate exactly what forces are actually acting on this box. So this box obviously has a weight, right? And the weight, as always, is a downward force. Right? This is the box's tendency to want to fall down, right, this surface towards the ground. Okay. Now, there's also going to be a force that opposes. There's actually going to be two forces that oppose this force vector, this weight. Okay. One is going to be the static frictional force, right? So I did a video earlier where I talked about the kinetic frictional force. This is the static frictional force. These coefficients tend to be just a bit higher than the kinetic coefficients of friction, right? And that's because it's it generally takes more force to get an object moving to begin with than it takes to keep an object moving once it already is moving. Okay, but the math of calculating the maximum frictional force, right, that a particular frictional relationship can produce in opposition to movement along a surface, right, it really isn't very different between them. Okay, it's just that this is a object that's already stationary, so we use the static frictional force. And that static frictional force is going to work in opposition to whatever direction of movement the object has a tendency to move, right, along this surface. So it wants to fall down. It wants to fall down towards the ground, right, parallel to this wall. And so the static frictional force is going to work in opposition to that, right, opposing that direction of movement. We'll call this, right, Fs. Okay. Now we can deal with this F. So this F is at a diagonal. And it's at a 30-degree angle with the surface of the box. So obviously, some of this force vector is in the x-axis and some of it's in the y-axis. And we will resolve those mathematically as we go on in the problem. So some of this, right, is going to be the x-axis. We'll call this fx. Some of it's going to be in the y-axis. Call that Fy. Okay. Now there's actually one more force that we haven't accounted for yet, right? So when we push an object down on a surface, right, and we apply a force to that surface, right, that is perpendicular to the surface responds, right, with a force in accordance with Newton's third law, right? It actually responds with two different forces, one parallel, that's the frictional force, and one perpendicular, that we call the normal force. Okay, so because the force that is perpendicular to this surface, right, is going to be F in the x-axis, the normal force is going to face in the negative x-axis, opposite F's x component. And there it is. Those are our force vectors. And let's just define, right, that's x in the negative direction. This is y in the negative direction. This is y in the positive direction. And just making room for a table over here. This is x in the positive direction. Okay? All right. So let's make a little bit of a table and let's define each one of these terms mathematically in both the x and the y axes. And then we can add them all up and set that entire summation to 0 and then use that to solve for basically what F is. Okay. So I'm going to make a table, and because I'm using PowerPoint as a whiteboard, my lines are going to be a little crooked here, but just bear with me. So we're going to describe each one of these in the x and then also in the y. Okay. And let me just erase this. I'm pretty sure you're all aware that this right side of the screen is the positive x axis. Okay. So let's define each one of our force vectors. We've got F. We have W. We have the static frictional force. Could have made that line straighter. And then we also have the normal force. Okay. Now to get F in the X and the Y directions, we need to resolve F basically, okay? So the way that we do that is we look at the right triangle that's being made between F and the surface of the box. Right? So in case you can't completely visualize that right triangle, let me help out with that here, okay? Here we go. Okay. So we have an X component right here. Right? We have a Y component right here. And you can think of F itself, just plain old F, right, as the sum of both these vectors and the hypotenuse of this right triangle. So if you think about it that way, this 30-degree angle between the box and F, right, is opposite to the horizontal component, right, which would be F in the X, right? So this is where we go to SOHCAHTOA. So SOHCAHTOA basically tells us that if we want the opposite, right, side, right, of this right triangle opposite to a particular angle, well, the sine of theta, or the sine of a particular angle in a right triangle, right, is equal to the opposite divided by the hypotenuse, right? So if we want then the opposite, then all we need to do is take the sine of theta and multiply it by the hypotenuse, which would be F here. So F of X ends up equating to F times sine 30, okay? And this is positive because F in the X is facing in the positive X direction. Right? Now we can go to Y, and we see that the Y component, this vertical component, is adjacent to this angle, right? And what does SOHCAHTOA tell us about that, right? It tells us that the cosine of theta is equal to the adjacent over the hypotenuse. Again, the hypotenuse is F, right? So if we want the adjacent side to this angle, we can just take the hypotenuse and we multiply it by the cosine of theta, the cosine of 30. So Y ends up becoming F times the cosine of 30. All right, moving on to W. What we can say about W, without a doubt, right, just by looking at our free body diagram over here, is that all of W is in Y and none of it is in X. So for X, W gets a big 0. And for Y, right, well, W in the Y, right, would simply equal, right, the box's mass multiplied by gravity, multiplied by G, which is 9.8. So when we take 40 kilograms and we multiply that by 9.8, well, we get a weight of 392 newtons. And that's going to be negative because that force vector is facing in the negative Y direction. Okay. All right, so moving on to friction. Again, static frictional force is going to be one of these forces that does not exist in the x-axis. So again, we're going to say that this is 0 in the x-axis. And then the y-axis, right, it's basically going to equal, right, the maximum frictional force that can be possibly produced by this frictional relationship, because we're trying to put as much of this weight, right, on the frictional relationship, right, because we're solving for the minimum force, the absolute minimum force that we can apply without it moving. So this, right, the Fs max, basically, right, maximum frictional force that can be produced by a particular frictional relationship, right, is going to be equal to the coefficient of static friction multiplied by the normal force, right? Okay. So we are then going to have, when we have a static coefficient of static friction, we have it at 0.35. Then we need to multiply that by the normal force. Well, what's the normal force going to be? Well, look at the normal force on the free body diagram. Normal force is just a force vector that opposes, and if you remember what normal force basically does, it matches, right? It matches whatever force is applied perpendicularly to a surface, right? So Fn is basically going to be equal to the x component of F. Okay, so it's basically going to be 0.35 multiplied by F times the sine of 30. So this 0.35 multiplied by F sine 30. Okay. Now, let's go on to, and again, this stays positive, right? It stays positive because the static frictional force is pointing in the positive y direction. So now our normal force, right, in this case, does not exist in the y-axis at all. So again, we're going to put a 0 here in the y-axis. And then in the x-axis, right, it's basically just going to be the negative of the x component for f, okay? It's just going to be basically f sine 30, but negative. So negative f sine 30. And if you use your imagination a little bit, you can probably see already how it makes sense that the sum of all the forces in the x-axis, right, they're definitely going to be 0. The only forces we have in the x-axis are the x component of f and the normal force. And it's basically just this minus this, right? Of course that equals 0. Okay. So now that we have all of this, we can just kind of accept the fact that if I add this and this and this and this and this, it should equal 0. And then we can just do a little algebra, and we can use this to determine what f is, basically, okay? And if you go down here, right, this is basically what we just did. We took stock of all of these force vectors, right? Everything that's externally affecting this object. And then we're just kind of accepting that fy plus fx plus fn plus fs plus w will equal 0, okay? And we can simplify this even more, right? Because we don't actually need to put the x variables into the equation. We already know they're going to cancel out. We can simply say the sum of all forces in y equals 0, right? And then solve for f, right? And that should be sufficient. So basically what we're going to get here, is 0 is going to equal f cosine 30 plus f sine 30 minus 392. Okay. Sorry, again, like that looks like a 4-year-old wrote it, but I'm hoping that you get the idea there. And I can just, I'll write it on a different 2. Write that 2 a little better. All right, there you go. It looks like a grown-up wrote that too. Okay, so what we can do is we can combine these terms. These two f terms are like terms. They're like terms, okay? Oh, excuse me. Sorry about that. F times the sine of 30 times 0.35. Myself a little bit of room here. Minus 392. Okay, now we're good. Okay. So what I can do here is I can take the cosine of 30, right? That's basically the coefficient of this f. I can take sine of 30 times 0.35. That's basically the cosine or the coefficient of this f. And then I can just combine these two f's. And what I end up with is, I'm going to do that on my calculator real quick. Okay, so the cosine of 30, okay, plus the sine. So the sine of 30 times 0.35, okay, plus cosine of 30 equals basically, so 0 equals f times 1.04 minus 392. Okay. Make myself some room by getting rid of this thing right here. Okay, since we've moved on from it. Then you can probably see what we can do from here, right? We can just add 392 to both sides and then divide both sides by 1.04. And we end up with f equals 392 divided by 1.04. And see what that equals, 392 divided by 1.04. And yeah, so from that we end up with about 377, okay? 377 newtons. Okay, so this is the minimum force that you would need to apply to this box, right, in order to keep this box from moving down this wall, right, moving at all. Okay, so 377 newtons, so yeah, so this box, right, basically weighs 392 newtons, okay? So 392 minus 377, okay? So about 15 newtons of this box's weight is being supported by the frictional relationship here. And then the rest is being supported by the actual F, right, that is being applied to the surface. But this is a technique that will come back and back and back with lots and lots of different basic physics problems where you basically just add up, right? Well, first you define exactly what external forces are affecting this box. You think about what their sum should equal, right? Sometimes it'll be 0, sometimes it'll be non-zero. It'll be non-zero when there's an acceleration. Then you just need to calculate exactly, okay, given the acceleration, what should the sum of all these force vectors equal, right? And then once you have that equation, it's all just algebra from there. You can just solve for the thing that you do not have. And sometimes that sort of evolves into some sort of 2x2 system of equations, right? So we'll always have this x and this y axis, right? So you saw that we were able to break this up into two different equations. We didn't need the sum of all forces in the x-axis equation, but sometimes that can help in terms of just forming a substitution that you can then use to solve for a particular variable in the y-axis equation. Okay, so I hope this all made sense, and thanks for watching.